So welcome everyone to the IEEE World Congress and Services. This is the third edition of the Future Financial Symposium. So good morning, good afternoon, good night, wherever you are joining today. So today we're going to be discussing forward-looking technologies applied to finance, and specifically we'll talk about quantum computing and the challenges to introduce a new technology into the market, especially when we're talking about a disruptive technology like quantum. And to do this, we have a distinguished speaker, Dr. Roman Orus. He will give a presentation on the quantum computing, the challenges. He'll give his experience of the company that he has launched, Multiverse, specialized in quantum for financial services. And he'll share the type of solutions that they have developed. He'll talk a bit about the clients. So Roman, he's a research professor at the Donostia International Physics Center in Spain. He's also co-founder of Multiverse Computing, and he's specialized in developing quantum algorithms for the financial sector. I will be joining him at the end of his talk. We'll have a live discussion on some challenges to introduce a new technology into the market. We'll follow Jeffrey Moore's technology adoption curve and talk about a bit about the characteristics of the clients, what do they have in common. So this discussion is targeted to those companies that are considering adopting quantum computing. This will help them to think about what do I need to do depending on their profile, depending on what type of company you are, what's your appetite for innovation, how you should approach quantum computing. My name is Elena Yndurain. I'm a professor at the IE Business School. I'm also a technology strategist. I'm focused in launching new technologies into the market, and I'm currently working in quantum computing. So with this said, I'll pass it over to you, Roman, so you can, if you want to add something a little more about yourself before taking the presentation, please do so.
Hey, thanks a lot, Elena, for the very nice introduction, and also thanks a lot for the invitation to give this talk. I'm really honored. Let me share my screen. Let me see. Okay, here it is. So yeah, that should be working. Let me know if it's working or not. Should be fine. Okay. So yeah. Excellent, thank you. So thanks a lot for the as I said, for the very nice introduction. So, well, I'm here to explain you about the current status of quantum computing today, not from the theoretical point of view, but not from the application point of view on how quantum computing is starting to be applied to industry. All right, and I will show you some specific cases, okay, in particular those related to finance, in which, as Elena said, I've been working in person together with already with some clients, okay, financial institutions, banks, and so on. All right, so this is an interesting topic, I think, because this is, is a new technology, and we are just witnessing the first adoptions of this technology into industry, and I think we are living with some very interesting times in this respect. So let's start. Okay, this is the reason why. This is the reason why we are here today, which is that quantum computing is actually jumping into business. So for many years, quantum computers were regarded as something very academic. Okay, they were on essentially research experiments on university labs and so on. But in the last years, let's say in the last 5-10 years, there has been a very fast development of some experiments and also some technologies, and this has helped to create, like, I mean, it has boosted the technology a lot. Okay, in particular, there has been a lot of money coming from private companies. Let's say, for instance, as I'm showing here, Google, Microsoft, IBM, Alibaba. Also, Fujitsu, all these people are investing many hundreds of millions into developing a working prototype of a quantum computer, right? And there are also many startups appearing. Some of the most interesting ones, let's say, are well-known, Rigetti Computing, for instance, D-Wave, Xanadu in Canada, But also, interestingly enough, also geopolitical regions are investing billions on quantum technologies. Okay, so for instance, Europe is investing several billions on quantum technology flagships. We know also that the Paris region is investing around 1.8 billion euros on quantum technologies. Germany itself is investing around 2 billion euros and so on. The US also is investing several billions. China is probably investing 10 times more than the rest of the world together, or even more, and so on. So there is a lot of money flowing into quantum technologies. It means that there is this is, of course, helping to make rapid progress in experiments, and there are good reasons for this, as I will show you in this talk. This is because quantum computing, and in particular quantum technologies, they are a new paradigm of how we are going to process information, okay, in a more efficient and reliable way. And it's essentially going to think the way, it's going to change the way in which we think about computations and about problems, okay? Now here you can see what we have nowadays. For instance, this is an example of one of the quantum computers at IBM. I think this picture is a couple of years old, but nowadays a quantum computer or a quantum processor is something that is as big as a whole physics laboratory. So we should compare it to the status of, let's say, classical computers in the 1930s. Say when Alan Turing devised the first, let's say, Turing machine, it was like a whole room. So nowadays, or the ENIAC computer, it was a whole building at the very beginning. So nowadays, we are in the same age, I would say, of quantum computers, where the first prototypes that we are just building, they are actually whole labs. All right. Okay, so let's move on. We are going to be talking about adoption of quantum computing in industry. So maybe it's worth starting talking about what is quantum computing all about. All right, so let's see. Well, quantum computing is all about using the laws of quantum mechanics to process information, allowing to do calculations that are otherwise intractable. So quantum mechanics is a part of physics, okay, that deals with the most fundamental building blocks of nature. So you know, atoms, molecules, photons, which are the particles of light, okay, superconductors, topological materials, these type of things. They are the most fundamental pieces of nature, okay, that we know in our physical understanding of the universe. And they don't obey the usual laws of physics that we know. They don't obey Newton's laws. Okay, they obey. This was understood in the 90s. Okay, in the early 90s by many people. They just obey a different set of physical laws. These are the laws of quantum mechanics. And it turns out that in time we have understood that we can use these laws to codify information directly in these building blocks of nature. We can codify information in atoms, on atoms, for instance. Okay, and we can use that to build a computer that is able to do calculations that with our current classical computers, classical in the sense that they are just the computers that we've been building since the 1930s, okay, will be impossible to do. All right. Now, this idea, as it sounds like science fiction, but actually it was proposed many years ago. So one of the early adopters of this idea, and actually the pioneers, he had this very long-term vision, was Richard Feynman. So Richard Feynman is a very well-known physicist. He was Nobel Prize because he developed quantum electrodynamics, which is the theory of the interactions between light and matter. Okay, it's one of the finest theories of how nature works. He got the Nobel Prize for that, but he was a very clever guy, and he actually, he did many other things. And one of the things that he did around the 80s was to actually understand that, if you have to simulate nature, of course, is quantum mechanical. Okay, materials are just obeying the laws of quantum mechanics, all the atoms in a material, all the molecules, and so on. And if you want to simulate that, if you try to do it with something that is not obeying the laws of quantum mechanics, which is, for instance, a classical computer, and I mean, of course, it's not going to work. It's going to be very hard to simulate. Okay, so if you want to simulate nature, since nature is quantum mechanical, you better do it with a quantum computer. Okay, you better do it with a machine that is obeying the laws of quantum mechanics. That was, let's say, the idea that Feynman had. Later on, I will tell you that Feynman was actually not the first one to think about this, but this is the right intuition. So if we want to simulate nature, we better do it with something that obeys also the same laws that nature is using, okay? And nature is using quantum mechanics. So we should build a computer using quantum mechanics. And that's a quantum computer. Now, what's quantum mechanics? For those of you that don't have a very strong background about this. So quantum mechanics, as I said, is the most fundamental physical theory that we have. So it's the physical theory of objects at the Planck scale. So the Planck scale is a scale of essentially energy times time. This is what we in physics call the action. And it's a very small scale. It's something of the order of 10 to the minus 34. You can see it here. So it's really, really tiny. Okay. At some point when you start reducing things, the standard laws of Newton, they just don't work anymore. And you have to start thinking in terms of some other equations. And these are the equations of quantum mechanics. In terms of length scale, this is the physics that shows up, let's say, when we have something of the order of 10 to the minus 35 meters. This is super tiny, all right? Now, the Planck length is precisely this number here, 1.616 times 10 to the minus 35 meters. Quantum mechanics tells you that this is the shortest meaningful distance. Below this distance, there is no notion of geometry at all, okay? Just the questions that don't make any sense. Now, what is quantum mechanics? Well, it's a theory that regulates how molecules, atoms, electrons, photons, superconductors, superfluids are behaving. And you can see here a scale, okay, a logarithmic scale that tells you how deep we need to go into nature. So if a person is the size of the order of 1 meter, then we start going into, cells, atoms, the nucleus, and so on. So as soon as we start dealing with molecules, let's say, and also with very complicated objects, but if they are of the order of, let's say, 10 to the minus 9, 10 to the minus 10 meters, then we have to use quantum mechanics. So if we want to simulate molecules, if we want to simulate atoms, if we want to talk about atomic nuclei, if we want to talk about nuclear reactions, and so on and so forth, it only makes sense if we use quantum mechanics, all right? Now, many of the predictions of quantum mechanics are very counterintuitive. Perhaps some of you have heard about, all these stories about Schrodinger's cat, that quantum mechanics is full of paradoxes, that it tells you that there should be many universes, so on and so forth. Well, quantum mechanics is complicated to understand. We still don't have a clear interpretation of what the equations actually mean. This is a matter of, this is a field of research on its own nowadays. It's called quantum foundations, okay? But physicists nowadays, they just have a very pragmatic point of view, and they say, well, these are the equations. I'm not gonna think about what is the meaning of these equations deeply. I'm just gonna use them to predict the outcome of the experiments, okay? And this is what we do in physics, and surprisingly, quantum mechanics works all the time. And in essentially more than 1 century already, there has not been one single experiment that contradicts the predictions of quantum theory. Okay, so quantum mechanics is actually the most tested physical theory in history. It has never failed. It has never been contradicted by a single experiment, and this is very significant because as I'm highlighting here, if you go to a particle accelerator nowadays, such as the LHC that is in Geneva right now, they are doing just collisions of protons against protons. They are doing this at a rate of 600 million collisions per second. And every single outcome of those collisions every second, as we are talking right now, is actually in agreement with the predictions of quantum mechanics. Every single one of them. It has never been found a single experiment that contradicts the theory. Okay, so this is the rate at which we are testing this theory, and it's always correct as far as we can check. All right, so it's a very deep theory, and we have also understood that we can also use it to codify information. Now, this is a little bit of a timeline of quantum mechanics, okay, in history. The theory started around 1900s with, there was a problem in physics. It was called the problem of black body radiation. It's a very simple problem. Perhaps you never thought about that. But for instance, when you are at a fireplace, okay, and you see the ashes, okay, the ashes, they are red, okay, and then somebody had this question, where does this light come from? Okay, so the light comes from inside of matter. because it's just emitting this light, but it means that inside of matter there is light. But how can this be? Okay, so physicists like to think about this type of crazy questions, and at some point they mathematize it. They try to understand it with thermodynamics. It was a total failure. And then Max Planck had to come with a theory and actually an hypothesis. It was called the Planck's hypothesis, and was able to explain the spectrum of radiation that you obtain in this type of situations. And this was in the 1900s, more or less. And that was essentially when quantum mechanics was born. He had to make some assumptions that energy came into discrete packets. Okay, that was the quanta, and therefore came the name of quantum theory. All right. Afterwards, there were many developments. Einstein studied and explained the photoelectric effect and the structure of the nucleus, the structure of the atom, internal degrees of freedom of fundamental particles, such as spin, the wave-particle duality, that sometimes fundamental particles behave like particles, sometimes they behave like waves, and so on and so forth. Okay. Now, there was a very famous conference. This picture actually here is very famous. You will never see so many Nobel Prizes together as in this picture. This was the first Solvay conference in 1927. You can see here Marie Curie, Lorentz, Einstein. I think Heisenberg was also here, and so on. All the fathers of quantum mechanics were in this picture. I think half of them actually got the Nobel Prize in different years in physics. Okay, so that was the early days of quantum mechanics. And of course, after that, there were many developments. We used quantum mechanics to understand better materials. We use quantum mechanics to understand better the interactions of particles among themselves, and so on and so forth. And quantum mechanics is the reason why we had so much technological development in the last century. Okay, but around the 80s, we understood something else, which is that, well, looking deeply at the equations of quantum mechanics, it's not just a theory about how the universe works. It's actually a theory of information. So this was realized around the 60s and the 80s. Okay, Feynman, as I was telling you before, he was one of the first ones that understood that quantum mechanics was all about information, and also Yuri Manin, a Russian physicist. Afterwards, there were some early developments. David Dodge, he proposed in 1985 what will be the minimal requirements for a universal quantum computer. Okay, and around the 90s, so the people already understood that with codifying information in fundamental units of quantum systems, one will be able to manipulate information in a different way. It was still not understood whether, this could be more efficient or not. But then around the 90s, there were several developments that were very important. First of all, in 1991, there were developments of quantum cryptography, how to do cryptography that is unconditionally secure using quantum systems. And then in 1994 and 1996, there were the two first, let's say, important quantum algorithms. The first one was the Shor's factoring algorithm, which is the one that is essentially putting at risk, let's say, our crypto systems nowadays. All right. And also Grover's algorithm for searching in unstructured databases. Grover, he actually proved that it was, if you had a fully working quantum computer, you will be able to search in databases much faster than what you can do with a normal computer. Okay. Now, this started the field really because, of course, these problems, they showed that if somebody was able at some point to build a quantum computer, it was not just a matter of academic interest. This will have some very important industrial applications. Okay, using Shor's factoring algorithm, you could just decipher all the secrets that are flowing through the internet. Okay, and this, of course, is worrying many governments, right? So the topic is serious, all right, and we discovered that in the 90s. After that, of course, the people started around the early 2000s to have the first working prototypes with some technologies that nowadays we are not using, such as nuclear magnetic resonance and so on. Also, at IBM, they started having a 7-qubit quantum computer. Around 2010, 2011, we started to have the first serious attempts to build a quantum processor. In particular, D-Wave was born. This was a company. It was the first quantum computing company trying to commercialize a quantum computer. Okay, and then after that, already this was around 2017, and then over 2020 and so on. We already know a little bit the story. It developed very quickly. We started to have more and more powerful quantum processors. Nowadays, we have around 50 something or 60 something qubits on quantum processors by IBM, Google, and other companies. So, it's developing very fast because governments and private companies, they just started to put a lot of money into these technologies because they realize that they have a lot of potential. Let me explain you why quantum computing is something that is going to change the way in which we actually compute things. Now, this is a very simple example. It's imagine that we want to solve the factoring problem. Now, factoring is very easy to understand. Imagine that I want to just factor a number into its prime decomposition. Okay, so for instance, 15 is equal to 5 times 3, as we have here. But now, instead of doing it for 15 or for 21, which is 3 times 7 and so on, which is very easy, imagine that I give you a number that has 670 digits. All right, this is a very large number. Now, this is a typical number that we use in RSA crypto systems nowadays to codify the information that, for instance, when I do a transaction with the bank and I want to pay something via PayPal, for instance, so all this is, ciphered and secure and so on. So this is the type of protocols that we are using nowadays so that there is nobody stealing the information of my credit card. Okay. Now, this protocol is secure because factoring is a hard problem for a classical computer. So the best classical algorithm for factoring a very large number, it takes around 10 to the 34 steps, all right? Which on a standard computer, terahertz with 1 trillion operations per second and so on, it will take around 300 trillion years. This is much longer than the age of the universe. So you can understand that, of course, this is not very practical, and therefore, we can think that this is not a problem that we can solve with current algorithms on classical machines. However, if you have a quantum computer, you could solve it in just 8 hours. And this is because, as I was saying before, Peter Shor, who is, well, we have a picture of him here. He just came up with this algorithm in the 90s that has a polynomial complexity instead of exponential as the best classical algorithm. And, it just takes 10 to the 7 steps. It means that with a quantum computer that works with megahertz clock speed, which is essentially the one that is achieved, that can be achieved nowadays, it will take around 8 hours to factor this number. So of course, this is telling you that, well, we have this problem of high technological impact, not just mathematical academic impact, but it also has an impact on how society works. And it turns out that if we ever have a working quantum computer, we have to change the way in which we are just doing this. Okay, it's going to change the way in which we are codifying information. All right, it's a change of paradigm. So with quantum computing, we can do things that with classical computers we cannot do. Okay, so in the moment in which we have a working quantum computing with many qubits, which is the fundamental unit of information in quantum computing, it means that, well, we are going to have to rethink the type of things that we can calculate and the type of things that we cannot calculate. Okay, it's essentially going to shake all the foundations of computer science. All right, now this has been known, as I told you, Shor's algorithm is from the 90s. The original idea of processing information with quantum systems is actually from the 80s. So we are in 2021, and then the question is, well, what happened? Why we didn't think about this before? Okay, why there is a hype, let's say, or this, why everybody's talking about quantum computing right now? Well, the reason is that now we are starting to have the first prototypes of quantum computers. They are small, they are noisy, they are not perfect at all. They are not as big as we would like them to be. But they are the first prototypes, and we can start playing with them and doing things with them. And in some cases, as I will show you later, we can start applying them to actual real problems in industry. Okay. Now, Google, a couple of years ago, claim that they have achieved something called quantum supremacy. Now, quantum supremacy is the point at which we can solve a problem with a quantum processor that we cannot solve in any possible way with all the resources that we have using conventional classical computers. All right, it's essentially the singularity point, the breakout point, the point at which you are able to solve a task with a quantum computer much more efficiently than with a classical computer. All right. Now, this was claimed by Google in the essentially a couple of years ago, 2019. All right. There was a paper out there. It was super famous. They did it actually with this processor. It's called the Sycamore processor. So it was a processor based on superconducting qubits. All right. And it was a transition point. Nowadays, it's still under debate whether actually Google reached quantum supremacy or not. There have been some people claiming afterwards that, well, what they did could actually be simulated using some specific techniques or not. But what is clear is that we are at the point in which, quantum supremacy may actually show up, and we may actually be able to solve problems that are not possible to be solved using classical resources. Okay. So that's the reason why everybody's talking about quantum computing nowadays. All right. How does a quantum computer look like today? Well, in case you didn't see a quantum computer yet, this is an example of a quantum computer today. This is actually one of those quantum computers by IBM. It looks like a lamp, okay, but it's actually a fridge. All right. So all this structure that you see here, it's actually a refrigerator. It's cooling down the temperature. So you have essentially room temperature up, and then the temperature goes decreasing as you move down. All right. Now here at the bottom, essentially, we have millikelvin temperatures. This is 10 to the minus 3 Kelvin. Is around 10 to the minus 5 Celsius or even Fahrenheit. Okay, it's super cold. It's colder than interstellar space. All right, so it's one of the coldest places in the universe. Okay, and that place is where we just attach our quantum processor. This is an example. Okay, it's quantum processor deal with superconducting qubits, which is one of the type of technologies that we are testing nowadays. And this is an example with 4 qubits, excuse me. So this is one of the first quantum processors that were built by IBM. So that's how a quantum computer looks like today. Now, this is not just the only type of quantum technology, let's say, that we are using to build a quantum computer. There are actually different types of quantum hardware proposals. The field is still evolving. We still don't know what's going to be the standard for building a quantum computer. We know how to build a classical computer. Nowadays, we build it with semiconductors and so on. But in quantum computing, there are many, many proposals on how to actually build it. Superconducting qubits is just one of them. Now, other proposals involve, for instance, ions on ion traps. So, an ion is just an atom for which we remove one of the electrons. And then the remaining part is actually an atom less with one electron less. This has an electric charge, and it can respond to electromagnetic fields, and we can trap these ions. Okay. Now, by building an ion trap, we are also able to build quantum processors. There are proposals for building quantum computers using ion traps. There is a very famous proposal actually by Ignacio Cirac and Peter Zoller already several years ago. This is an example of how these ion traps look like. They are inside of a huge vacuum chamber in a huge lab. Inside of that vacuum chamber, you have a chip, and inside of this chip, you have some radio frequency trap where you are actually, trapping your atoms. Okay, so this is a picture, for instance, where you can see four ions. Okay, and each one of these ions is actually one quantum bit. All right. Nowadays, we can do much better than that. This is an example of 51 qubits trapped on an ion trap, and you can see each one of these qubits is one atom. Okay, so I don't know if you ever saw the picture of an atom, a single atom. Here you can see 51 of them one by one. Okay, so you can already start understanding that this is a technological feat. So it's something really difficult to achieve. We are making pictures of atoms one by one, and then we are also controlling them one by one, and we are making them interact in the way that we want them to interact. So this is a technological achievement, and that's the reason why it's something very complicated a priori to do, and that's the reason why it took so long. Okay, but this is the status right now. We can do this with current technology. We can manipulate all these atoms in this trap. We can make them move. We can make them interact. We can control them atom by atom via lasers and so on and so forth. Now, all this is very nice. But why should quantum computer be interesting from the let's say industrial and business point of view? Well, this is very, very well summarized in this square here. All right. Here, this is one of those magic quadrants by Gartner. Gartner is a consultancy company that is very famous. It's for making these quadrants where you can see a lot of information organized in a very interesting way. In this case, each one of these points is an application of a quantum computer, or let's say an algorithm. Now, in the horizontal axis, we have the time to market. So the time that it's going to take for these algorithms to actually reach the market. Let's say there are some algorithms and some applications that need very powerful quantum processors. These are going to be long-term applications. No? Some other applications are going to hit the market sooner because they actually need smaller processors. They are not so demanding, let's say, and therefore they are going to come sooner. Now, in the vertical axis, we have the business impact, okay, or the speed up. So how is going to impact, business. This type of applications. And you can see that there are some applications that, of course, they are going to impact a lot the businesses. For instance, Shor's algorithm for factorization, it's obviously in cybersecurity, it's going to have a very big impact, but it's, it's towards the long term because we still need very powerful quantum computers for running that algorithm. No? However, and very interestingly, there are some applications that already come in the short term. Okay, and I think there are two applications that are particularly important. The first one, everything that has to do with optimization. Okay, and then second, everything that has to do with artificial intelligence. For these two types of applications, we can start applying the processors that we are developing right now for real problems with real data and in real situations. Okay, so for quantum optimization in particular, we have quantum processors such as the one built by D-Wave that can be applied in combination with some hybrid algorithms that are half classical, half quantum, but we can start applying them to actual real life problems, not just toy models. This I will show you towards the end of this talk. And everything that has to do with artificial intelligence, surprisingly, doesn't need very powerful quantum processors. There is, everything has to do with machine learning. There is a whole version of that uses quantum mechanics. It's called quantum machine learning. And it turns out that it provides new algorithms that are more efficient. They are also more precise, for instance, at doing anomaly detection or fraud detection and so on, at detecting subtle patterns of anomalies, let's say, in the data. These type of algorithms actually are very robust against noise because they are heuristic, same as neural networks, okay, that they are also heuristic, but surprisingly, they also can work very well with quantum processors that are not so powerful, that they are not so big, such as the ones that we have nowadays, okay? Because many times it's not just about the speed up, but it's also about the precision or being able to detect or recognize interesting patterns in the data. So this we can do with the quantum processors that we are starting to have right now. So of course, this is going to have a huge business impact. This slide is already 1 year ago, so I think it's outdated, but there are of the order of 200, 300 new startups every year on quantum technologies. And the prediction is that in a couple of years, the global market on quantum technology will hit around 13 or 14 billion US dollars. But probably this is underestimated by now. This number, I think it's going to be bigger. Okay. So quantum computing is coming and it's going to affect business. Okay, that's the message. And it's happening right now. We're just starting to see it. Now, where can we apply quantum technologies in industry? Well, in many places. Of course, material science. So as I told you before, if materials are done by atoms and molecules, we better use quantum computing to simulate them. In finance, as I will explain you in a second, finance is full of complicated equations that are very hard to solve mathematically, and also using, we have some of the brightest minds in finance dealing with equations that deal with money, the market, and so on. And still, it's very difficult to predict, very difficult to understand, and so on. So that's precisely where quantum computing can offer something. Chemistry, of course, for developing new molecules, pharma, for developing new vaccines, for instance, that are based on complicated molecules and so on, proteins and so on and so forth. Optimization problems that have zillions of applications in logistics, in smart manufacturing, in mobility, wherever you want, all right? Machine learning, the same, pattern recognition, fraud detection, essentially all the applications that we have nowadays of machine learning, they can be improved using quantum computing. In communications, of course, because we can have more secure communications by using quantum technologies, for instance, using quantum cryptography, and so on. I mean, usually I like to say that these are the applications that we can see right now, where quantum computing is going to have an impact. But I always like to say that the application of a quantum computer still has to be discovered, because for finding the actual, let's say, killer application of a quantum computer, we first need the quantum computer with us, okay? This would be like saying, like asking Alan Turing in the 30s what will be the most important application of a Turing machine. And then he will probably say, well, this for deciphering the messages of in the Second World War and so on. He would have never thought about Twitter, let's say, or about social networks. So this is the same question. We cannot think of the analogous of Twitter for quantum computers because we still don't have a quantum computer. So first we need a quantum computer. 100 years afterwards, we'll see what we are going to be using it for. Okay. Right now, we understand that we can use it for lots of things, and this is the reason why we need to build this machine. But I think it's going to bring a lot of surprises, and once we understand and we have the machine with us and we understand it better, we are just going to find out that it's useful for many other things that right now we can just not imagine. Okay, so what about finance? Well, in finance, there are lots of applications of quantum computing. Who should be interested? Well, banks, of course. Also finance departments of very big institutions, rating agencies, regulators, and essentially everybody that is using algorithms to understand how money works. Okay, people working on quantitative finance, the guys that are building your pension plans, trying to maximize the profit and minimize the risk by the time, so that by the time that you retire, you have some savings, and so on and so forth. All these people are using very complicated algorithms because the equations involved are actually very, very difficult to solve. Okay, they are using Monte Carlo, they are using optimization algorithms, they are using machine learning, they are using essentially everything that is possible. All right, they have also some of the best and most powerful supercomputers in the world. And anything that has to do with new algorithms that are more efficient, of course, it's interesting for the people in finance. They are just eating algorithms. They are consumers of algorithms. Okay, so this is the reason why finance is a good place to start. Now, in this context, we built Multiverse Computing, which is a startup that we were mentioning at the beginning. We do quantum and quantum-inspired computing for finance and economy. I will tell you later what quantum-inspired means. We have appeared in several places, for instance, in Forbes, in The Economist. We are also in the Tech Council of McKinsey, also in reports by IBM, Boston Consulting Group, and so on. And yeah, we had this intuition that, well, we can apply quantum computing for finance, and let's make it very clear what can be done and what cannot be done. Okay. Now, this part of the talk is going to be more about the business side. Okay. This is a one-page summary of actually Multiverse Computing. We are in San Sebastian and Toronto, and also we are opening an office in Paris. We are just closing funding round of around 10 million. We operate as software as a service because you can program a quantum computer, okay, using your personal laptop. just by downloading the libraries that you have to use to call the quantum computer to do the operations. Okay. Now the quantum computer is always on the cloud. All right. We control it from the laptop through the internet, but we program it directly from here, and then we run the operations on the cloud. Okay. Good. So we have proprietary quantum and quantum-inspired algorithms. Right now, we are around 27 people with 10 PhDs. We were the first in the world to demonstrate the usability of current quantum processors for real problems in finance, so not toy models. We work with real data, and people are starting to put money on this, and also to to get ready. We closed around 1 million euro in contracts in 2021. So this is an indicator for a startup that things are moving very well. All right. Now, this is our idea of how to use quantum computing in industry and succeed in the quantum revolution today. Of course, the summary of this is the following. We have what we have. We have prototypes that are limited. Okay, they are noisy, they are small. We can just not do everything that we would like to do with them. Okay, we cannot factor very large numbers and break the RSA crypto system. Now, does it mean that quantum processors nowadays are useless? No, that's our point of view. You just need to use these quantum processors for the applications that they can do. Okay. Now, this is the same situation as if we go, let's say, to the 80s, and we ask Bill Gates, let's say, okay, can you do a voice recognition system with a PC? And he will tell you, well, no, I cannot do that, okay? Because I don't have, my computer is not sufficiently powerful, the algorithms is very slow, the memory, blah, blah. Okay. Now, what can you do with your PC? Well, I can do a spreadsheet. Well, a spreadsheet. Okay, is that you say, this is boring, no? But is it useful? Well, of course it's useful. It's Microsoft Excel, so we use it every day. Okay, so we are exactly in that situation. We have to find the right application for the hardware that we have nowadays. Okay, and this is what we are doing at Multiverse Computing. So, in our opinion, first, we think that quantum computing is ready if you select the application wisely. Okay, this is point number one. Of course, you cannot factor very large numbers, but probably there are applications for which these prototypes can already be used. All right. Now, to succeed, you must deliver the solutions in a way that is ready for production. This is very important for companies. Okay, so the middleware is mandatory. You cannot ask the people in the banks, let's say, or the people in doing, I don't know, smart manufacturing or whatever. You cannot ask them to be experts on quantum physics. You cannot. I don't know. They are working on their own problems. Okay, so they need a middleware that is able to translate their view of the world, okay, to the actual problem in the quantum computer. Okay, so middleware is mandatory. You cannot ask them to directly program a quantum computer. You need to make it easy for them. All right. Now, third, very important, you must focus on very specific applications, okay, that are good and not in bad universal solutions. You need to focus on very targeted problems. The spreadsheet, okay? You don't want to build Microsoft Windows. You want to build the spreadsheet, okay? You want to build Microsoft Excel. Let's start with that and then we'll see, all right? And it has to be easy. This is super important. You cannot ask, I don't know, I cannot ask my mother to program a quantum computer, okay? But I can ask my mom to I don't know, to run Microsoft Excel. Okay, so this is something that has to be easy of using. We have to make it easy. Okay, now why finance? Because it's a very good place to start. It's full of problems. Okay, there is a lot of money. Banks are very interested, and so on. This is a perfect place to start applying quantum computing in industry. And yes, there are lots of users. Okay, that are willing to prove whether the technology works. We are building our solutions in a software package that is called Singularity. Okay, Singularity SDK. It's a middleware. It contains our algorithms that we are patenting. It takes care of, connecting to the quantum computer, running the thing on the cloud, coming back, offering the solution, and so on. Later on, I will show you a 2-minute video of an example. Now, the nice thing about Singularity that I think is something that I think that we at Multiverse did very well is that it's production ready. We are implementing it directly in the production line already of some financial institutions and can be used as software as a service. Now, here is where you can apply quantum computing in finance. a summary. You can use optimization algorithms, okay? You can apply quantum computing right now on optimization. Now in finance, there are many problems that are based on, that are based on optimization. For instance, optimal trading trajectories and portfolio optimization, which is the problem of how should I invest my money in order to maximize returns in 20 years, all right? And minimize risk, also training of traders, ETFs. If you know about investment, you probably know about these words, but this is about replicating indices, replicating the NASDAQ, for instance, with just 5 assets. ALM, capital allocation, and so on. So there is a lot of very interesting problems here that are very hard. Now, everything that has to do with quantum machine learning, again, pattern detection, fraud detection, for instance, all the algorithms that have to do with distinguishing, cats from dogs, but applied to finance. Credit scoring, you go to the bank, you ask for a loan, and they tell you, well, let me check your background. And then they check your background, and depending on where you live, what is how much are you earning, what is your position, blah blah blah. They give you the loan or not. Okay. Now, what is deciding there is a machine learning system that is actually scoring you. Okay. Okay. From 1 to 10, how reliable is this guy? And I don't know if I go to the bank, probably I'm not reliable. If Elena goes, she's very reliable. So they are gonna, it depends on a system that is rated. Okay. So this can be also be improved with the with quantum computing. Also, things related to marketing, customer buying propensity. What are customers gonna buy? Okay, this can also be this is a very important problem, not just in finance, insurance, of course, fraud detection, credit card fraud, anti-money laundering, tax fraud detection, anomaly detection. Anything that has to do with machine learning can be improved with quantum computing. Third, very important, pricing. This is something specific of finance, which is predicting the price of very complicated financial objects. Okay, financial derivatives, financial options. There are some very complicated equations there, such as Black-Scholes equations and so on. There are even Nobel Prizes for this in economy. Now, solving these equations is very complicated. People do it with neural networks, with solvers of partial differential equations, with Monte Carlo. They do lots of different algorithms there. There is a lot of money also here, and people in finance, people that do the traders, for instance, and people doing quantitative finance, they are extremely interested in this problem. And this is also somewhere where quantum computers can bring a speed up, all right? Last but not least, simulation of the economy. Now, simulation of the economy is something that sounds like science fiction, but actually with a quantum computer, we can simulate small financial systems, okay? And one may think, well, if there are not many agents in a financial system, why should this be interesting? Because the financial networks are huge. And yeah, it's huge, it's true, but sometimes they are not so huge. For instance, the financial network of central banks in America is not so large because there is Central Bank of Canada, the European, if you include Europe, there is a European Central Bank, then the Central Bank in the US and so on, and maybe it's a network of 10 or 12 people and that's it. Okay, this is already extremely hard to simulate, and with a quantum computer, you can also bring an advantage here and predict the impact of a measure, whether it's gonna shake the economy or not, and so on. Right. Now, here on the right-hand side, you have an example of how quantum computing is seen as valuable for the people in finance. Okay, on the left-hand side, it's a problem of fraud detection. Essentially, this is accuracy on detecting fraud for credit cards. As a function of, for different types of models. Essentially, all the blue dots are standard machine learning algorithms. The red one is a quantum machine learning algorithm that we devise. It offers a 2% extra of accuracy. And you may say, well, this is very small. Well, yes, it's very small. But when you translate it into dollars, for a bank of the size of Citibank, is around 80 million per year of savings. Okay, and then we are talking. Okay, then we are in business. Now, on the right-hand side is about optimizing portfolios of investments. Now, typical investment portfolios, they offer a return that is not particularly optimal. Okay, whereas with a quantum computer, you can find much better optimal trajectories of investment as a function of for the same risk, essentially. Okay, so these are two places where we can offer valuable solutions to people in finance. Now, the type of solutions that we are offering, they are based on quantum computing. We use superconducting qubits, photonic qubits, very different types of quantum hardware platforms, also Rydberg atoms. There are companies and startups that are building quantum processors based on this, also trapped ions and so on. We also offer quantum-inspired solutions that are solutions inspired. They are classical, they work on classical processors, but they are inspired by how a quantum computer is actually processing information. They can be deployed right away. We don't need any hardware to become mature, and they are actually being found as very valuable by the clients. And some of them we are world experts, such as tensor networks. We are programming them right now on GPUs and also FPGAs, and they offer speed ups and also improvements in memory that are very, very significant. Some clients that we've been working with, you can see that some of the people here are actually well-known. BBVA, one of the top 47 banks in the world, Caixa and Bankia, they just fused to Spanish banks. They are also right now very large. One of the tax agencies in Spain also, on fraud detection. CACIB, Crédit Agricole, one of the biggest banks in the world and also in Europe, well, in Europe and also in the world. Okay, in France, we are working in a couple of projects actually here, having to do with rating fallen angels, it's called the problem, and also pricing. Okay, Repsol, okay, the energy company, we are working with them on some problem related to energy markets, which surprisingly is very similar to finance. And also the Central Bank of Canada, we are doing some pilot projects also with them related to, well, simulation of economy. Example, optimizing portfolios of investments. This we did with BBVA. We also did it with CaixaBank and Bankia. It's a problem of, we actually wrote 2 or 3 papers on this together with them. This is a problem of astronomical dimensions. It's intractable by conventional technologies. So the type of products that are being produced by people in financial institutions, let's say by your broker, okay, they are suboptimal, okay, and using, quantum computing, and in particular, using D-Wave's quantum optimization machine, okay, which is a quantum annealer, we were able to solve for the first time this problem on a quantum computer in a real life situation. For instance, first with Bankia, we did optimization with 52 assets over 8 years. With BBVA, and with Bankia, it was 50 assets over a 1-year period. So these are, optimizations that they are not toy models. Okay, these are the types of optimizations that traders and brokers will just implement in their daily life. Okay. We actually, it was highlighted, this type of optimizations in several places. This is a highlight by D-Wave, actually, this company producing the quantum hardware. You can also download it here in this PDF. It's pretty well explained. The questions that we have to optimize the cost functions, they were extremely complicated. They had a lot of constraints. And the last thing that we did was to do the optimization using the full SP500. So, the SP500 is the set of the 500 biggest companies in the US. The index that is, averaging over how all these companies are behaving is called the SP500. It may go up or it may go down. And then you may ask, okay, in which company should I invest and in which company should I not invest in order to maximize my returns? Okay, so this is a problem of absolutely astronomical dimensions, investing in 500 companies. Okay, a portfolio optimization for such big numbers has never been achieved, and we are actually able to do it with quantum computing. Not just that, but as I told you before, middleware is very important. So right now we do it through Microsoft Excel, connecting to the quantum computer on the cloud. So let me show you a video so that you can see how we are doing this.
Multiverse Computing Singularity makes quantum computing really easy for the inexperienced user. Singularity allows you to unleash the power of quantum computing directly with a click and assuming no previous quantum knowledge at all. For this, the team at Multiverse have connected quantum computers, working on the cloud as a backend, to really simple and intuitive front ends. Our vision is to implement quantum computing directly via these tools, so that it can become a part of the production line of any financial institution. Singularity allows you to connect powerful quantum computing directly to your favorite spreadsheet. Let's see how our quantum powerful portfolio optimization algorithm works. Spreadsheets like this are used by analysts to deal with financial data and obtain the products that are sold to clients. After installing our plugin, we just need to specify the relevant input data, like returns and volatilities of the assets, and other parameters such as total investment and investment bands. After clicking Start Optimization, Singularity takes care of designing the optimization problem, sending it to the quantum computer on the cloud, getting the results back, and displaying them in a user-friendly way. As you can see, optimizing the full S&P 500 takes just a few minutes with Singularity, whereas it is a never-ending task with other state-of-the-art algorithms. Moreover, the obtained portfolio also provides higher returns than standard simplified solvers, which gives suboptimal solutions. And it's as easy as just one click in your spreadsheet. Singularity is quantum powerful and as easy as pie.
Well, I hope you like it. Here we did something, as I was telling you before, middleware is very important. So what we understood that many people working in quantitative finance directly, the traders, the people that are in production, they are actually using Microsoft Excel very intensively. Okay, and then we thought, okay, we need to connect a quantum computer to Excel because this is the tool that they are using, and that's exactly what we did. Okay, now here it looks very easy. You just run a quantum computer by clicking. In a menu that you can get just by installing our plugin. It looks like super simple, but behind this, there is a whole product being built that is super complex. It's building the optimization problem, sending it to the quantum computer on the cloud, solving there, coming back, displaying it in a user-friendly way, and so on, as the video was explaining. So this is the type of thing that we need to make quantum computing accessible to the broad audience. Okay, we cannot ask them to program quantum algorithms. We need to do it for them, and then we need to provide them with this type of tools. Okay, and here was for portfolio optimization, but actually it's the same for all the other applications. Sorry. Now, in the last 5 minutes, I want to say a couple of words about other applications of quantum computing beyond finance. Of course, in chemistry, nowadays, people can simulate some very large molecules also using D-Waves, quantum optimization machine. Okay, in particular, there is a company in Toronto called OTI. They are very good at simulating molecules up to 500 qubits. These are materials that are already relevant for industry. With IBM quantum computing, with IBM's quantum computer, also there were some early works on simulating some molecules with very few qubits. Okay, nowadays I'm pretty sure that this can be done for larger systems. Mobility, there are many partnerships between quantum computing companies and automotive, such as Mercedes, Volkswagen, Ford, Toyota, BMW, and also some others. Why? Well, because they have also many computational problems that can be solved more efficiently with quantum computing. Not just about traffic optimization, which is the typical problem, but also about designing new battery cells for electric cars, new catalysts for reducing emissions. Also for self-driving vehicles, getting better artificial intelligence algorithms for detecting patterns and being able to avoid collisions and so on. Planning routes for delivery, also for minimizing traffic jams in cities. There are many proofs of concept actually in this subfield, okay, which are very interesting. And I invite you to have a look at these references down here. So since this is being recorded, you can feel free to have a look. And if you are not able to find them, just feel free to contact me. Okay, but for instance, there are some very well-known examples of Volkswagen with D-Wave. For instance, they optimize the routes of taxis in Beijing, for instance, for going from Beijing downtown to the airport. Okay, using a quantum computer in real time. Cybersecurity, of course, with a quantum computer, we can crack all current crypto systems, and therefore we need a new cryptography standard. This is called post-quantum cryptography. Okay. There are many proposals for this, and as far as I know, the NIST and also the US government, they are looking for what is going to be the next standard. There are several proposals there. Another solution is to use quantum cryptography. So actually there is a way of doing unconditional communications by using quantum systems. Some people are very advanced on this. For instance, the Chinese, they have satellites up there that are sending quantum particles to remote locations, and therefore they are establishing quantum channels to do cryptography. There was a very famous example, a very famous experiment a couple of years ago, I think, between Vienna and Beijing. They were able to transmit information between these two places using, a quantum channel. And of course, quantum computers, in terms of cybersecurity, since they offer better quantum machine learning algorithms, they can also be better at, threat detection and also spam filtering, phishing detection, detecting viruses, and so on. Logistics and smart manufacturing, traffic of ships, traffic of airplanes, optimizing routes. This is something where quantum computers can also be very useful. Also in the ground, seaport optimization, the optimization of loading and unloading of containers, the optimization of loading and unloading an airplane, and this type of problems that, companies spend lots of millions at the end of the year because of inefficiencies in these procedures. So quantum computing is also very helpful with that. If you want to learn more about the commercial landscape of quantum computing, feel free to have a look at this paper. It's around 1 year old already, but I think it's a very good place to start to learn about what is the commercial landscape of quantum computing. This is a very nice review on Nature Reviews Physics. Now, the point is that, of course, there are unending possibilities. So if you have a very hard computational problem, that you think, well, the solution is by far not optimal, probably I could do it much better with some other algorithm, than think about quantum computing, because probably quantum computing can do something for you in that respect. Okay, so with this, I would like to conclude. I think I'm on time, and thanks a lot for your attention, and I will be very happy to discuss with you about anything that you want to discuss. Thank you.
Thank you very much, Roman. That was a very interesting presentation. So we're going to go ahead and start discussing a bit more the technology adoption. So if anyone has questions, please feel free to include them in the chat, and we will add them to our discussion. So I'm going to share here the. Okay, so to help us in our discussion, we're going to talk about the usual technology consumer segmentation. So if we think about the consumer segmentation for technology based on Geoffrey Moore's his segmentation, there are two big categories, right? One is the customers that want technology and performance. And then the other division would be those that actually just want solutions and convenience. Now, the challenge is how to write this curve, how to convince each of the customers to adopt the technology. So what are their needs, and how do you address those needs, right? So if, for example, you're launching, like this is the case with quantum computing, a new technology that is not fully working, and you try to go to that second half of customers, the ones that want solutions and convenience, maybe that's not the right segmentation you should go to. But it's important to understand how ready is the market. So what are those customers thinking about, and how is your technology working, right? So if we think about these subcategories, so like the innovators, they're tech enthusiasts, they'll try any technology because they want to see what's happening. Those early adopters, they're visionaries, they see the potential. And then there's the other big category of the majority. That's where we want to go if we want the technology to be successful, right? If we want the technology to be adopted, we must go to the majority. But those are pragmatists and conservatives, right? So they don't really, they're not interested so much in those technology innovations, although everyone thinks they're an innovator. But then the question is, are you willing to invest money in R&D to test? That's the big question, right? Do you have a budget for R&D? And are you willing to test the technology that's not fully working? So if we apply this to quantum, right, when we think about the evolution of quantum, like Roman was explaining, how it has evolved, everything since I would say 2010, so 2015, that's when we started seeing the big changes, right? So when IBM, for example, opened up the quantum computer to the world, to the cloud, companies started testing it. So we started seeing the proofs of technology, how companies were testing the technology to see how it worked. And then right now we're in the phase where we are seeing a lot of proof of concepts. Roman gave us a lot of examples of that. And as the number of qubits evolves, right, we see the yellow line here, which is the evolution of the number of qubits. Every day there's a new announcement of a higher number of good quality qubits, which is a promising indication of how the technology is proving that it's working, right? So based on this framework of the proof of concepts and how we get use case creation for business, I'd like to ask you, Roman, based on your experience, right? You've worked with a lot of companies, you gave us some examples. What would be the common characteristic of those companies that you've worked with? Like if you had to say, you know what, to define a profile, what would the profile of that company, of a company that tests quantum computing is?
Yeah, so yeah, that's a good question. So the typical common characteristics and profiles of the people that we've been working with. So these are typically, say, big companies, as you saw, like big banks such as BBVA or Caixa or even Repsol, which is not a bank, but it's also a very big company, no? Or Crédit Agricole, no? Where you know they have some very intensive, they have a big department on computer science, let's say, and then they are trying to innovate. Okay, so the people that are approaching us typically are the people from innovation. Okay, the people that are trying to find new solutions to all problems, and they are trying to start testing the technology. So they typically build a subgroup of people that, let's say, okay, this is going to be our quantum group, and these guys are going to try to identify what are the relevant problems that we have inside. And we are going to, I don't know, allocate a small part of our resources into doing some proof of concept into something, and then we'll see if this is useful or not. So this is a typical profile of the people that we are working with right now. So people that want to test, they want to be pioneers on using the technology. Okay, that's essentially what we are finding right now.
And when they work with you, do you always work in a mixed team model? So you work hand in hand with them, or are you finding companies that want more of a turnkey solution, like just come over, you do the test and give me the solution and let's see what happens?
Yeah, we're actually finding
the way of working that you've seen.
We're actually finding both of them, but I would say we are finding more that they want to work with mixed teams. But this is very typical of banks, okay, where they have their own quantum team, and then we say, okay, we can already provide solutions and so on, but they want people from inside to get involved in the project because it's going to be useful for them for a number of reasons, no? Because you train their people, then their own people also they learn how to use the technology and so on. So typically they want to get involved, so it's a mixed it's a mixed solution. I mean, with some of the people that we are working, we typically have a weekly meeting with our technical team and also their technical team, and then we coordinate who does what and how do we do that and why and so on. That's a typical situation. That's also the way that's also what works better in our opinion. Because this is very special especially for the banks. They want to learn the technology, okay, and then of course they want to involve their own people, okay, because at some point they want to become independent or whatever. Now, having said this, there are also examples. So we have also found a few examples, but they are not the majority of people who actually they just, well, we don't know, we let you work and you provide us the solution and then we'll see. Yeah, this can also be the case. Okay, but in this case,
more or less, if you think about the whole spectrum of your clients, how many have wanted to do that? You do it turnkey versus combined.
I would say combined is 90%. Yeah.
90%.
Yeah, we also prefer that option. Yeah, because it works much better. Yeah. Because otherwise, then you work more closely with the client, and then you understand better what is exactly what they need. Because otherwise, you have always, if they give you total freedom, you have the risk of developing something that in the end they are not going to be using. No, and yeah.
Right, and also if you think about it, if you do that way of working, it's not really a way working that you do in the innovation phases, right? That's more when the technology is ready and then you hire someone to you outsource it, right?
Exactly.
I guess speaking of that, so what is the star, type of use case? So this use case that's most demanded when companies want to do this proof of concepts. What is the number one?
In finance, there are two. Actually number ones. So I will say both of them. Yeah. So one is optimization, portfolio optimization.
Oh, you mute.
Yeah. Oh, I muted.
No, you're not. Sorry.
Okay.
No.
So
I lost you for a second. Yeah.
Okay. So we have two. One is portfolio optimization. I think that this the reason why they are focusing on this is because the problem is very clear. And there are already several papers and works on that. But then there is also another application which they are asking us very often, which is pricing. This thing that I said about pricing of financial derivatives.
Yes.
This is the problem that everybody wants to solve. Yeah. Now, for this problem, unfortunately, we believe that quantum computers are still not ready to solve real-life situations because the algorithms that you need for that, they may involve a larger number of qubits. But since everybody wants that, we are thinking very hard about how to provide solutions in some way or another. Okay.
Then you mentioned you worked hand in hand with companies in mixed team. What is the profile of the people that are selected to work in quantum in corporations? Yeah. What profiles are you running into?
They are technical people. Okay, and we are surprised that many times, for instance, inside of banks, there are many physicists working, okay, as quantitative analysts and so on, because they deal a lot with equations and with computers and all that. And we always find some physicists hanging around. So they are typically physicists, mathematicians, programmers, that real hardcore programmers. Okay, these are the type of people that we are finding. Okay, now. Typically, you find these people in the innovation departments. All right. Now, in some cases, we are also talking directly with the guys in production, and there you find essentially lots of technical people and also computer scientists. You find a lot. Yeah. So it's but these are not people that necessarily have a background on quantum computing. So for them, it's also. Quantum mechanics is not something that you learn by watching a couple of YouTube videos. I usually say that, and therefore it takes some time to train.
Definitely not.
Yeah.
Yeah, that's why I was asking, because it's the skills, right, that you need is not like, in my experience, I've worked with many other technologies, and obviously quantum it's a different story, right?
Yeah.
And you need to learn it. You need to study it. It's not, you're not migrating a system to quantum. You have to rethink it, and you need to rethink it from the quantum lens.
No, so, it's a different way of thinking.
Yeah. Since you've been working for a while with companies, have you seen how long does it take to someone who's not a quantum physicist to learn and to be able to contribute when you do this joint work? This
That's
technical, of course, we're the basis is that we have people that have a strong STEM background, but those that are not, they don't come from quantum physics. I'm sure they're able to catch up, but how long does it take them? Or actually, are they able to? I guess the first question is, are they able to catch up? And if so, how long does it take them to do it?
I mean, it's relatively easy to catch up in the sense of being able to run your first quantum algorithms. Okay, so if you have a strong mathematical background, let's say linear algebra and so on, then you can learn the rules of quantum mechanics and take them for granted and don't think too much about what that means physically. And then it's okay. So somebody tells you, well, these are the new rules for computation. Okay, and then you just learn what can be done and what cannot be done, and you learn to program that using Python libraries and so on. That this can be achieved in a few months. Yeah. Now, a different story is understanding really what is going on, so that you can develop new quantum algorithms. And for that, you need at least to spend some time of the order of 1 year at least or more. Yeah.
Yeah. I had heard that it was more or less like 2 years to be able to.
Exactly.
I mean, dedication. And I guess the last question, since we're getting to the end of our allocated time. If we see this chart here, where do you think companies are right now? Because I mean, if you think about the segmentation, I think we've run out of innovators. and those that are early adopters. So where are we? What's your guess?
I think we are in between, let's say, in between POC and learning for organizational readiness. This is, I will say that this is more or less achieved by quite a few people already, especially in the last years. But we are starting to see some business benefit in some specific examples. So we are getting towards the top of the mountain, I would say. Yeah, we are somewhere in the middle.
We're like
more
over here,
or less,
right? Like starting to get in the early majority.
Yeah.
So what are the applications that we're starting to see the business benefit?
Well, optimization. Okay,
Optimization.
And in finance we are seeing portfolio optimization. Yes, and also quantum machine learning. So things that have to do with fraud detection, credit card fraud, anti-money laundering, and so on.
And when you talk about business value, this it means that companies have they already deployed this? These algorithms. Do they have deployed and running side by side with the classical?
Yes, and they are outperforming in some cases what they are doing. Yeah.
And is there any public information you can share that?
Well, in some cases some people are starting to put it in production.
But okay, that's as far as you can read. That's okay.
That's okay.
But that's really good news. That's fine. It's actually really good news to see that we are starting to see with the current technology. Because what would you say is a threshold in terms of qubits, given the quality of qubits we have, right? What's the threshold to get to that business benefit? So to this part here in the middle, what is this qubit, this yellow?
I mean, I will say that 100 qubits, but it's not just about how many qubits you have, but also about how well you can use them. Okay. So right now, one of the limiting factors is also the noise. So we could have a processor with 1,000 qubits already, but we need to be able to operate on those 1,000 qubits very often and so on.
This yellow, it's supposed to be quality. So meaning not noiseless, obviously, but working well enough.
So 100 qubits with a very good accuracy will be a game changer, in my opinion. Yeah.
Okay.
And nowadays we have around 60, 70 qubits, but the noise level is still not at the point where we can, we can do things, but we need better quality qubits.
And because we hear a lot of quantum volume, right? Only like Honeywell recently announced a huge number, right? 1,000 of quantum volume. What is in your experience, and not to mention Honeywell in particular, but what is this quality qubit?
I think
what would it be?
Every company is able to find a quality measure that just fits their processor. Okay, so that's also something that if you go to Honeywell and they say, well, we have a very large quantum volume, well, okay.
So the quantum volume goes per company. Okay.
Yes, not just the volume. I mean, also the accuracy. So what?
Right.
I don't know. I wouldn't be able to quantify it, but if I were able to, let's say, have a 100 qubit system that has a really small error, and also one is able to operate it with a super small error per gate and so on. Right. Now I'm not able to quantify it right now on the top of my head, but that could already be very useful. Yeah.
And the lower, what's the lower you would think that we would need? What percentage? When you talk about 100 qubit, 0.1.
No, less than that. Much less than that. I mean, no. I mean, actually, some of these companies running ion traps, I know that they have 99.9% fidelity in some of the 2 qubit gates that they are using, and still that's not sufficient. So we need much more than that for running very large. Exactly. So if you have many qubits, you have to be able to operate on all of them, and therefore you have to run very large computations, and the error has to be super small. So, yeah.
All right. So then, actually, those 100 qubits could be error-free. So they.
Yes, as much as possible. Yeah.
Almost as possible. Okay. All right. Okay. Well, thank you very much. This was very useful and very encouraging also to see that we're starting to see problems that are being deployed, even if they're small, right? but that's a huge difference from like 2 years ago. So well, with this, we're going to stop the recording. Thank you very much for your participation. And hopefully we will have another conference soon, and we will be talking about real size problems that are fully deployed.
Thank you.
Well, thank you, and have a good day.
Thank you. Bye.